Before we address the meaning of the actual magnitude of the standard deviation, you might have noticed something funny with the two standard deviation computations. With the population standard deviation, you divide by how many elements there are in the population. But with the sample standard deviation, you divide by one less than how many data points are in the sample. That seems rather odd. You would think this one would also be lowercase n. However, we want an unbiased estimator. So S is an approximation of sigma. Sigma is the standard deviation of the entire population. This is what's desired. But usually we don't have access to the entire population due to costs or for legal reasons or time. So instead we settle for the sample standard deviation, and we want that to be an approximation of the actual population standard deviation. However, we want that approximation to be unbiased. And ultimately what we mean by that is we don't want S to typically come in below the actual population standard deviation sigma or above. We want it to be fluctuating around that, but rather close. And in general, if you have n here, this estimate, if this was n right here, this estimate S is typically an underestimate of the actual population standard deviation. So that means it's a biased estimator. We don't want a biased estimator. So to make it an unbiased estimator, statisticians figured out that we needed to take one less off of the sample size. So now, with this formula, this is an unbiased estimator. So it's an unbiased estimator of sigma. Now we can start to address the meaning of the standard deviation. We saw in a previous video that a larger standard deviation implies the data is more spread out. So the larger the standard deviation, the more spread out the data is. The smaller the standard deviation, the less spread out the data is. So, but what does the number itself mean? We can't actually answer that as easily as we could for the range. For example, in one of the problems in the previous screencast, we had a group of salaries that had a range of $35,000. That $35,000 meant specifically the difference between the highest salary and the lowest salary was $35,000. We can't do it so simply with the standard deviation, but we can in a more sophisticated mathematical way. And that more sophisticated mathematical way is dependent on something called Chebyshev's theorem. Chebyshev's theorem is very important, and ultimately it says this: the portion of any data set lying within k standard deviations, but k has to specifically be greater than 1, of the mean is at least 1 minus the quotient of 1 in k squared. So before we can get to actually applying this theorem, we got to figure out what in the heck it is even saying. So what I want to first do is let's find out what 1 minus 1 over k squared is for some typical k values that you would see in problems. Well, the most common ones you would see are k equals 2 and k equals 3. So 3 standard deviations away and 2 standard deviations away from the mean. Well, if I plug in that 2, I've got 1 minus 1 over 2 squared, which is 1 minus 1/4, which is 75%. And if k is 3, we've got 1 minus 1 over 3 squared. 1 minus 1/9 is 8/9, which is approximately 88.9%. So let's reread the theorem now, plugging in k equals 2 and then k equals 3. So Chebyshev's theorem says the portion of any data set lying within 2 standard deviations of the mean is at least 75%. The portion of any data set lying within 3 standard deviations of the mean is at least 88.9%. So within 3 standard deviations, at least, and the key word is at least there, you can see I've bolded it for a reason, at least 88.9% of the data. And within 2 standard deviations, you have at least 75% of the data. And there's one other word here that is I've highlighted, specifically of any data set. So ultimately, let's go back to something we've done previously. What this is basically saying, whether you have a perfectly symmetric data set, a highly skewed left, a highly skewed right, something that doesn't fit nicely at all, looks like this. No matter what, whether you're dealing with this scenario, this scenario, this scenario, this scenario, this theorem always holds true. So within 2 standard deviations of the mean, at least 75% of the data is found there, and at least 88.9% of the data is found within 3 standard deviations of the mean, whether you have this sort of data distribution, you have this, or this. Let's actually now see what this looks like in application. So what can we say with Chebyshev's theorem? Suppose a standardized test in mathematics has mu equals 72 with sigma equals 7. We want to use Chebyshev's theorem to make a claim about the percentage of scores within k equals 2 standard deviations of the mean. And notice it says nothing about how the data is distributed. Maybe it's symmetric, maybe it's skewed left, maybe it's skewed right, maybe it's none of those. Remember, Chebyshev's theorem applies to any data distribution, so we don't even need to know that. So again, the population mean of the test was 72, and the population standard deviation was 7. We want to use Chebyshev's theorem to make a claim about the percentages within k equals 2 standard deviations of the mean. So we need to first go 2 standard deviations above the mean, and then we also need to compute what's 2 standard deviations below the mean. Right? This is the mean, and you add on 2 standard deviations means 2 standard deviations above the mean, and this would mean 2 standard deviations below the mean. Well, let's do those computations. We've got 72 plus 2 times sigma is 7, which is equal to 86, and mu minus 2 sigma is 72 minus 2 times the quantity 7, which is 58. These are 2 significant boundary scores within our statement using Chebyshev's theorem. Now also, we did this computation when k is equal to 2, and if you can recall in the previous slide, Chebyshev's theorem says there's at least 75% of the data within 2 standard deviations. So what this translates to with respect to this scenario where you're talking about a standardized test in mathematics, this means that at least 75% of the test takers scored between 58 and 86. So that's our claim. At least 75% of test takers for this particular standardized test in mathematics scored between 58 and 86. At least, it's key that you have the word at least there. It could be 83%. It could be 95%. It's at least. The 75% is a minimum. There's no less than 75% of the test takers' scores falling between 58 and 86. Now, to practice this again, you may want to go through this computation and specifically see if you can do it with k equals 3. That's going to change this percentage, and it's also going to change these 2 boundary numbers. Give it a shot.